Hello people, today I'm showing you a quick tutorial on how to create a random set of floating leaves. So we're going to use Kangaroo and a bunch of plugins just for some, let's say, tweaking inside the simulation. The core of the simulation will be based on Kangaroo 2. Actually, you see here I placed also the whole set of plugins that I am using. So it's Heteroptera, of course, and Kangaroo 2 and Weaverbird, but just for the final refining of the meshes. Okay, so the result is going to be this kind of let's say small planes that you can give them the shape that you want. I'm just using flat square planes. But once you run the simulation, you will have this plane flying around. And you can also adjust the quantity, the amount of planes, and the wind direction, speed, and so on. Okay, so this is what we're going to obtain. I'm going to share this definition at the end of this small tutorial. You will find the link in the description. So let me first, let's get rid of this and let's go back to our initial file. So I'm going to create a bunch of random square meshes, and I want them to be oriented randomly in space as well. Because this way, when I'm going to apply wind and pressure in Kangaroo, then they will tend to fly away and deform in each one with its own specific behavior. So I'm going to create a populated 3D, and as I want to have this kind of wall of leaves, I'm going to specify a region as set1 box, and I'm going to create some kind of very thin and high box. And the population of points, I'm going to keep this low initially because the Kangaroo calculation can become quite heavy. I'm going to just use these points. In order to create some square meshes randomly oriented in space, what I'm going to use is a random vector. And this random vector is going to be a Heteroptera component. Well, actually not random vector because I don't need a specific length, but a random direction. And the amount of random vector and random direction is going to be coincident with the amount of points that I am using. So if you want to take a look at what's happening here, I'm going to grab a vector display and visualize this vector with correspondence to the anchor points. You see that each one is oriented randomly in space. The advantage of using Heteroptera in this case is that not only you have access to this kind of automatic let's say vector creation like I'm doing right now, but also if you take a look at my previous webinar and tutorial on the randomness in Grasshopper, each time you change this, you are going also to change not only the amount of points but also the random direction for your vector. So each time you change something in your definition, you will have a totally different behavior during the simulation with Kangaroo. Okay. So I will use this vector in order to create some normal plane having the origin correspondent to the random population of points and the z-axis defined by the random vector. So finally I get this kind of orientation. Remember that these are frames, these are not physical surfaces. So I'm going to create a plane surface starting from this plane. So I'm going to take their orientation, and I'm going to define a smaller size for these little surfaces here, like this one. But remember that you can always create any type of surface with any shape once you have these frames already randomly oriented. Okay, and I want to convert them into meshes because you know that Kangaroo works with meshes. And well, actually, if I do this exactly like this, you see that as I specify the x size and y size with one single value, and this is asking for a domain, then the surface, the square surface, will start from the origin of each of these random planes and occupy just the positive quadrant of the coordinate system. So if you want to these planes to occupy a central part of this frame, and so let's say that I want to create this plane around the origin of each frame, Then you can use a symmetrical domain from Heteroptera. Once again, you specify that the length is going to be this value. So this is going to determine the total width and height of your plane surfaces. And the base is going to be 0. So you create a symmetrical domain like minus 2.5 to positive 2.5. And then we can use this as the width and height for our surfaces. And you see that they are created around the origin of each frame. And so these are going to be our initial leaves in mesh configuration. I'm going to also turn on the preview of the edges. And U count, V count, we can set this like, I would use a small value for the U and V count. And eventually you will be able to decrease this if you want a faster simulation, or increase this if you want a more smooth deformation for each one of your leaves. Okay, so I'm going to keep this low actually. So this is finally the meshes that we are going to use in Kangaroo. And let's switch to Kangaroo 2. It's this one. So few goals for these meshes. First of all, I want to show the meshes after the simulation. So I'm going to grab a show component. Then I'm going to apply some wind force. And this wind is going to push horizontally, for example, towards along the x-axis. So I'm going to grab a unit x component. And I'm going to leave it like this because its factor is already set to 1, which is quite a nice wind. And the mesh I want to apply this wind to are all these planes. So I'm going to create a relay here in order to avoid crossing of wires inside this simulation, this definition. And then I want to apply pressure, and I want to apply pressure to each of these planes, but I also want to apply random pressures. So I want these leaves to be subject to a pressure that tends to inflate them in 2 different directions, considering the positive normal of these mesh planes. So I'm going to create a random number from Heteroptera once again. The amount of random values is going to also to be determined by the amount of points that I have created initially. So I have one strength for the pressure corresponded to each of the mesh planes. And if I do this, if I use random with absolute value, I'm only creating positive values for pressure. But if I set this to bipolar, I'm using also negative values for pressure. So we have the inflatable surfaces actually already defined. Remember that actually the first goal you should set up in Kangaroo is the elastic strength. So I'm going to give some elastic property to this mesh. Let me also wire display hidden this random here. We are not going to use it anymore. So I'm going to define some elastic property, and I don't want these leaves to stretch during the simulation. So I just want to set a strength. And I'm going to use a 5.00 strength in order for these bodies to maintain their consistency during the simulation and don't explode to pressure mostly. And then what else I'm going to place here? Well, basically I want these leaves to don't go below the ground floor. So I'm going to use a simple floor goal with quite a high value for strength, because this is the equivalent basically of an anchor point. So when you have this kind of constraints, I always recommend that you use a high strength in case of you are working with them. So there is no reason for using a floor if you allow some of the particles of your Kangaroo simulation to pass through the floor. Okay, either the floor exists or not. So if it exists, it is reasonable to give this goal a high value for strength. I think that's pretty it. You can also implement some other collision behavior with other objects and so on, but I'm not going through this during the simulation. So I'm going to use the entwine method, and I'm going just to use all of this thing here into one single branch, but the show component, which is going to travel by itself. And let's get also rid of all this. Well, this is the geometric system, as you will see in the final definition. Let's get rid of all the preview of what's already implemented here, and let's switch to Kangaroo Solver. So I'm going to use the standard toggle, the button, and I'm going to pass all my goals to the solver. Okay, so I don't want to see the preview of my particles and meshes and springs and so on. I just want to see the mesh result. So I'm going to tree statistics entwine, so to know what's the length of each branch, and I'm going to partition list the output of Kangaroo Solver. So we have this tree, which contains basically just the 13 planes that I am using and 1,431 goals that I'm using to determine the behavior for these meshes. So I just need the first branch of this new tree, and so I just do this, and here you have the meshes after the simulation. The rest is just refining the preview of the result for Kangaroo Simulation. So I'm not going through this last phase here. You can simply watch it in the definition. So once we have this set up, if you run the simulation, you will see that these planes start to fly around in a chaotic way due to wind and pressure as well. You could also avoid pressure eventually, but I find it quite nice to have also a random behavior, internal random behavior for this for these surfaces. Sorry. Okay, so that's it. You can play with the amount of vertices. You can play with the dimension of your leaves and the resolution of the leaves, and also how much deformable they are, because if you see, for example, that your leaves start to behave more like small textiles that tend to deform quite much, then you can increase the strength in order to avoid, let's say, try to avoid dramatic deformations. But also you could also work with some planarize in order to avoid excessive distortion or deformation inside the meshes. But anyway, this is something that you might want to implement by yourself. And then eventually you can also use Weaverbird, as I told you at the beginning, in order to create a better visualization for your mesh result. So I hope you enjoyed this little tutorial, and it's been extremely fast. I do recommend that if you have some doubts for what we have discussed today, you can also take a look at my previous tutorial, especially the ones regarding Kangaroo textile simulation, because most of the things that we have that we get for granted in this little tutorial are discussed in that previous 2 sessions. So thank you very much for watching this, and have a nice day. Bye.